Yeah, might have been like, but I mean, we have, yeah, we're going through the sim, trying to see like, what stuff should be, and if it isn't like live, and we like go to like the step before, on like, whatever will make it what it should be, and sit down, so I'll just start. And then keep on doing that until we get to the check, and then basically, like, we want to say, see if that fits it. It's like, rinse and repeat.
All right, so let's go ahead and begin today. So you can probably tell from what's on the board. We're going to talk about the stack segment, right? That's part of real memory. The only part of real memory we haven't talked about yet, right? Because remember the three segments of real memory. You get the code segment where the instructions are, then you have the data segment. We talked about data segment where we're talking about arrays, and then we have the stack. So we're going to start off with that, and then also talk about subroutines in some, and you'll see how that kind of ties into when you're doing subroutines. Okay, like I mentioned last class, I'll return the midterms when I'm done with the lecture, and I'll make some comments about the midterm at that time. Okay. All right, so first of all, let's start again. Like I said, it's stack, again, part of real memory. And what's below the stack? What segment's below the stack? That's the data, right? Again, it would be useful to have like your instruction manual handy, or also the lab manual that shows some of the things we're going to talk about. I put 2 hard copies on most tables. Every table got a hard copy of the auto diagram because I had enough of those. All but one table got a copy of this page that has the alternative register name. I'm going to be talking about those some more today. That table over there is the only one that didn't get that, but hopefully you got it on the computer. All right, great. Yeah, and then I don't have it drawn here, but the code segment is below the data segment. Now, where does the data segment start at? What address? 6,000, right? Because you needed to know that when we were doing arrays, remember? So this is, I'm just going to put the last 4 X characters. It's understood that, you know, the top 4 are all 0. Yeah. So yeah, data segment starts at 6,000 X. How about where the stack starts? You might have to look that one up because we haven't talked about it. But what address does the stack segment start at? What is it? Yeah, F then 30. Again, you know, the first 4 are zeros, and then the last 4 F 0, and it goes up to what address? Yeah, all of F's, the last 4. Okay, and I put this dashed line here between, and I'll explain why I, you know, picked the dashed line, you know, coming up. Okay, well, the first thing to know about the stack is that only words are written to or read from. Okay, we only write or read words to the stack. And you see, that's different than the data segment, right? Because when we were talking about arrays and talking about, you know, data being written to or read from the data segment, well, it could be words, it could be bytes, it could be half words. Right? Remember we talked about that because we spent time on, you know, how to figure out what address you're at for a particular, you know, type of data. Okay, so you see, as we go along here, one thing to keep in mind is that the reason why the stack has, like, you know, these particular you know, setup or the right words, construct, if you will. The way the stack is constructed is for simplicity. Okay, keep that in mind. That's one of the whole reasons for the stack is to make it simpler than how we deal with data in the data sets. And one way to make it simpler is we only deal with words for the stack, okay? The stack is byte addressable, just like the data segment is, and just like the code segment is, okay? But even though it's byte addressable, we still only either write or read words to the stack to keep it simple. Okay, there's another reason too that I'll get to later. Okay. Right from the start, keep that in mind. We want the stack memory to be simple, okay? All right, so when we write to the stack, it's called a push. Write to the stack is called a push. Okay. And when we read from the stack, okay, you all know the little bit mark means the same thing above it. When we read from the stack, it's called a pop. Okay, so that's just terminology that's specific to dealing with the stack. And to access the stack, we keep track of where the top of the stack is. And there's a special register that does this. And that's why I put the handout with all the alternative names. Because remember how we have those 5 special registers, of which 2 we're not going to use in this class. But one of them we've already talked about in quite a bit of length, right? The 0 register, X0. But there's 2 other registers that we deal with. And one of them deals with the stack. Which one is it? You'll be able to tell by the alternative name. Yeah, register 2, which is called the what? Right, stack pointer. So you see special register SP, which stands for stack pointer. Okay, which is register 2. That's the register that keeps track of where the top of the stack is. And it does this by holding an address. Okay. All right, so any questions up to this point? It's mainly nomenclature, you know, it's just some definitions basically up to this point. Then we're going to look at, you know, how like the stack works. Okay, but any questions up to this point? Okay, well, the stack is called a LIFO memory. Does anyone know what that acronym stands for? Did you see it anywhere else? Sometimes people have seen it in a different class. Right, exactly. Last first out. Yeah, there's also FIFO, right? First in, first out. Okay, but this is a LIFO. Okay, now for visualization purposes, this is how we kind of think of the stack, and this is why it's called the stack. Is that the words that we store in the stack, we think of them as being on top of each other. Okay, that we store something in the stack, right? And again, we only store words, like you said at the start. So like here's the first word that's stored, and then the next word would be on top of that, and the next word on top of that, and so on. Okay, so that's why it's called the stack. Okay. So I have a question for you. Because remember, like I said a little while ago, the stack segment, just like the data segment, just like the code segment, right? All of real memory is byte addresses. Right, so up here, you know, the last row of the stack. You know, this is gonna be all F's, well, 4 zeros and the last 4 all F's. Okay, then what's the address of this byte gonna be? This one's all F's, this is byte. All F's and an E, right? This is base 16. You guys should be familiar with this now. So what's the next one gonna be? All F's D. And what's this one gonna be? All F C. All F and the C, right? Now, I guess I should have mentioned this earlier, but when we fill the stack, we fill it in this direction here. So this is gonna be the first word, where we're gonna put the first word. So therefore, what is the first word address of the stack? Right, FFFC. Right, because again, we only store words in the stack, and since we're filling it this way, this would be the first word address. Okay, and you see that address is kept in the stack pointer register. And again, that's 2, right, register 2. Okay, so that's where we always start. We always start filling the stack from here. Is that clear? Okay, well, let's look at some example code. Okay, this is just example code to show how you would, you know, fill the stack and then how you would, you know, read from it. So the first thing that's typically done is that we initialize the stack pointer. So you've all seen this command before, right? Li is what? Load immediate. So we're just taking this value, okay, which is an address. Now notice it's an address that's just outside the stack, right? It's one above our maximum. Okay, but I'll explain why that's so, and you'll be able to see it as we go through this code here. But you see, we're just initializing the stack pointer to this value. Okay. Okay, then to push, right? To put data on the stack, which again, remember, a push is the same as a write, and a write is the same as a store. Well, to do a push, and again, we only put words in the stack, right? We only store words in the stack, so it's going to be a store word. So this would take the word from register T0 and do what? Because what does this tell us in this store word instruction? Right, the -4 is an offset. So it's going to take this offset, add it to what's already in the stack pointer, which is this 1 all 0. So if I subtract 4 from this, what am I going to get? FFFC. Right? If you take 1 and all 0s, subtract 4 from it, I get this, which is the first word address of the stack. Okay, so this is going to put the contents of T0 into FFFC. So the way we would think of that going to this picture is that the contents of T0, whatever word is in T0, would now be in this row of the stack. Okay, and you see the stack pointer is what's keeping track of the address. See, this is the top of the stack. Okay, is that all clear?
The stack pointer keeps track of FFFC or FFF?
No, it would have FFFC. Right, because FFFC is the word address. Right, and remember, you know, like we talked about before, you know, because this has to do with instructions in the code segment, and if we have a word in the data segment, that this address here, right, the address of the byte furthest to the right, that's the word address. And again, we only store words in the stack.
Okay, but you're loading into SP, right?
Well, remember, this instruction here puts this into the stack pointer register, right?
Right, so that stack pointer had, not, see. Where,
Well, at this instruction, the stack pointer has this in it, right? This one in all zeros.
okay, yeah,
Now it comes down to this instruction. What's this instruction gonna do? What's this part of the instruction gonna do?
well, it takes whatever's in SP and subtracts 4. It
Okay,
doesn't
so-
mutate what's in SP.
Say that
It
again?
doesn't change what's in SP. It just takes what's in SP, subtracts 4 from it, and then puts that in T0. Or T0 goes into that address, or
Oh, actually, let's see, let's look at the instruction. You might be right. If that's the case, you'll have to add an instruction.
yeah, it's in,
All right, let's see. So if you look at the SW instruction, store word, what does it say? It says the SW instruction stores a half. Well, that's gonna be a typo because it doesn't store a half. It stores a word in memory at the address formed by the sign pending and value of the function. The word then is stored in the value. Okay, the SW instruction does not change the contents of RS1 or RS2. So you're right, this would stay. I mean, this would stay 1000. It's gonna take the -4 from this and have FFFC. And then store that word there. But it doesn't make this change to FFC like you said. It will still keep this. So that means, oh, let's see. Well, that's okay though. That's okay though. It's only gonna change something at the very end. But still, what's gonna happen on this instruction is that T0 is gonna be stored at F. Well, you put that stored at. Right, it's gonna be stored at FFC. So you agree with that?
Yeah.
You're just saying that this
Well, just
actually
confused.
didn't change.
yeah, because you wrote SP and then it's pointing to
Oh.
FFFC.
So that was my mistake. I shouldn't draw that. That clears it up?
Yeah,
Okay, thank you. But you're right. Thank you. That was misleading, so. Okay, but now getting back to this, what's this next line gonna do? Yeah, it's gonna take T1 and store it where? Where is it gonna store? Well, this is a store command, so it's writing, so it's gonna take the data in T1 and store it here. Right? So this is gonna take T1 and store at what address? FFF what? 8. Which means in our diagram here, that would be right here, right? T1. Okay, but yeah, the stack pointer is still here. Okay, and then what would this instruction do? It's not an I, that's a 1. What is this instruction gonna do? Yeah. Okay, so these are all examples of pushes. Now, what could I do? What could I modify here? Not looking at the bottom yet, but still looking at the top here. What could I add? What instructions or instruction could I add so that my stack pointer always points at the top of the stack? Because right now, as what was mentioned earlier, the stack pointer is just staying here at 1, 0, 0, 0, 0.
Change the load immediate.
Say that again.
Change the load immediate.
Well, that would move it up here, but then it would also stay for the rest of them, right? But what I'm saying is, like, as we do pushes, how could we keep this stack pointer pointing where the top of the stack is instead of it staying right at 1 and 4, 0?
Not at the top of the stack. Isn't the top of the stack supposed to be cheaper?
Well, the top of the stack starts here, right? But we're going this way. So after we store something, the top of the stack would be here, right? Like after we store T0, we would want the top of the stack here. And then after we store this, it would be here. And then after we store this, it would be here. Right? Because the top of the stack represents where the data is coming into.
If we change what's in, the speed.
Yes, exactly. How could we do that? What instruction could we use to easily?
An item there.
Yeah, we could do an add I, right? That, let's see, where would we put the add I? We would put it like after each of the stores, right? So like right here, I could put an add I. And then what would I put? Add I, and then what? What do I put? Yeah, put SP, then comma, SP, and then what? So, what would I want to add to it? -4. Right, because that would take the 1,000 that's in the SP, add -4 to it, and then put the result back in SP. So this would make, you know, after this has been stored, this would move the stack pointer to here. Right? And then if I did it again after this one, right, if I did another add I, SP, SP, and then what would I put? -4 again, right? Because it still has, you know, the stack pointer. Right, it would still have this, so I just subtract 4 from that, and that would move it there, and then I do another add I here. The -4. Right, and then that would move the stack pointer there. Okay. Because again, with the stack, you always want the stack pointing to the top of the stack. Okay, so we would need those add I's in there. Okay, so any questions up to this point? Everybody see what's going on here? So, you know, this top half of the code is showing how we would, you know, push data onto the stack. Okay, the last part of the code here, it shows how we would pop. Right, so this is popping. Okay, so pops. And again, a pop is a word used specifically for the stack, which means you're reading from the stack. And this is where the last in, first out comes in. Right, so the last in, which is P2 in this case, that's going to be the first that's going to be read. Okay, so and we might have to make an adjustment here. Let's see. our stack pointer, no, actually, our stack pointer is right here, right, it's at that four. Okay, so what's gonna happen on this line here, this load word line? What is it gonna do? Because what's gonna happen here again?
Loads, whatever.
Yeah, again, what's happening here? It's taking this offset, adding it to what's already in the stack pointer, which is the FFF4. So it's gonna take the, it's gonna use this as an address. And take that data and put it into T2. Right, so. You know, the data. At FFF4 goes into. Register T2. Okay. And then this line here is going to take the data from where? Because what is this going to do now? What is this offset? What always happens to this offset and what's inside the parentheses? Yeah, it just adds it, right? So it's going to take 4, add it to FFF4. So now we're at FFF8. Use that as an address, take the data at that address and put it into T1. Okay, so this takes the data at FFF8 and it goes into T1. All right, and then this line is going to do what? It's going to take the data at FFC, and it's going to go into T0. Now, just like before, you know, our stack pointer is staying, you know, where it initially was here, but we want to keep it always pointing at the top of the stack. So just like we had to put add i's between these store word instructions, we're going to put, I'm missing some add i's here, right? Like I would have to put another add I here. And what would I want to add to my stack pointer at that point? 4. Right, so that would move it back down here. Then I need another add I.
Could you do that with the offsets instead of using the stack pointer? The first load word.
Well, you see, that's the mistake I originally made that Diego pointed
You
out.
could do it that way, but your first load word would be an offset of 12, and then you'd be looking at the top of the stack, just with the offset. So you always keep the stack pointer as the data, just with your offset.
I don't know, I'd have to look at it. I mean, there might be another way to do it, but I mean, I'm not disagreeing. I would just have to look at it.
Yeah.
But do you agree this works?
Yes.
Okay, and then this last add I, that would just get us back to the initial value. Okay, but the main thing I wanted to show in this example was to do pushes, it's a store word. To do pops, it's a load word. Okay, because pushes you're writing, pops you're reading. And the other thing is to show that whatever order you're pushing data onto the stack, when you pop, you do the reverse order, right? We went T0, T1, T2, and then because it's last in, first out, when you're popping, it's T2, T1, T0. Okay, and then the other thing is you always want to keep the stack pointer pointing at the top of the stack. Okay, now, this is all like, I'll get to your questions this way. This is all like basic, you know, and how to do it. The reason for it hopefully will become clear when we get to subroutines. Okay. But again, the other thing to keep in mind, and this is the purpose of the stack, is it's a simpler memory construct than say like the data segment, right? Because again, the data segment where you can store, you know, either a word, a byte, or a half word, and also it's, you know, it's in an array, so you have like an index. It's a more complicated way. The array version, what you do in the data segment is a more complicated, you know, memory construct, if you will, than the stack, right? Stack, you only have to worry about words, and you just got to worry about where the stack pointer is. Now, I'll get to your question just a second, but let me mention just a couple other things. Can you see that you would always want the number of pushes equal to the number of pops? Right? So you always want and can you think why you want them to effectively cancel out? Like what could possibly happen if your pushes and pops don't match?
Either try to read them somewhere, but they are available.
Well, the first thing he said is the main concern is that, remember, the stack is on top of the data. So if your numbers don't match, it's possible that eventually your stack could go into your data set. Okay, and that's what stack overflow refers to. Okay. It could also be that you go in Never Land because above the stack is like unreserved space. Okay, so like you said, you could end up, you know, say reading data that you didn't intend to read. Okay. See, remember, the data segment is typically filled this way, right? Like we did in our examples, right? With the data segment, we started at address 6,000, you know, we build an array going ascending. And as I mentioned before, the stack is filled this way. Can you think of a reason why they didn't make it where the stack started at this address and we filled that way? It goes back to, are these address ranges of our segments that are part of real memory, like our code segment, you know, data segment, stack segment, are those hard-coded address ranges? Are they set by hardware? No, they're determined by a program, right? A human being is what is determining those address ranges. So you see, by doing it this way, there's more flexibility, right? Because if you had a situation where you needed a bigger data segment, right? You didn't need that much of a stack. Well, it could easily be adjusted, right? This dotted line here could be moved up, or vice versa. If you needed a lot of stack room and not much data, you could move this line down. Okay, if you start to stack from here, you've essentially like hard-coded it. You know, not by memory, but by, you know, the program kind of hard codes it in a way.
So the line that you sort of just you're saying there's a line there.
Right, right. In fact, in the otter, see these address ranges for the code segments, in the otter, they're determined by code that's in the memory module. Like Dr. Hummel, yeah, if you look in there, you can find it. You can find the ranges. So you could go in there and change it. But the address range of real memory, the entirety of real memory, that's determined by the FPGA that's on the basis. That we can't change unless we got a different board, you know, a different FPGA. Okay.
Like will RARs not compile a program that tries to store? Like, if we tried to change the stack pointer to an address and data, or
no, as far as I know, and I'm 99% sure, yeah, RARs isn't going to give you any sort of warning. Like if your stack goes into your data segment, it's not going to tell you. Yeah, it doesn't have, again, I'm not 100% sure, but I'm 99% sure it doesn't have any like check in it like that.
So it's kind of imaginary, right?
Well, it's because the RAR simulator is, it's simulating the hardware. It's using the Otter hardware in the simulation. And as far as the hardware is concerned, these different segments, they have all the same hardware. Like it's all the same registers. Like there's no distinction in hardware between any of those segments.
Right, but you mentioned that in the code itself, you can go in and change.
Well, in the memory module that Dr. Hummel, designed, you can change these ranges. Like you could make your data range narrower, make your stack wider or vice versa. You can do that in the memory module of the Otter, but that doesn't, let's see, I guess if I'm understanding correctly, I guess your question is, does that correlate to RARs? Like if you do make that?
Yeah, I just, like, what part of the hardware needs to know what section is what section? If you see what I'm saying?
Well, as far as the hardware is concerned, there's no distinction between the segments.
Right, so
It
why
just-
code it then?
Then why?
Why have it in the code? Why separate the sections? If there's no
Well,
distinction?
Well, again, it's for the programmer, right? That, whatever they're working on, they can, again, adjust it to whatever their needs are. That's all. But they would still, the program would still have to be conscious where those limits are.
That's my question.
Yeah, the hardware doesn't, there's not like a hardware check where, if you go into a segment that you didn't intend to, that somehow flags. There's nothing like that.
So does the software check the limits or?
No. Again, not that I'm aware of it. Like the RAR simulator, that's what you're saying when you say the software, right? Yeah, the RAR simulator, as far as I know, like I said, I'm 99% sure it doesn't have any sort of check.
Well, if you try to pop, you go first on the first break, or,
Say that again, please. If you pop up.
first try to pop, you go first, or you go break, or one still alive.
Okay, so you're saying like we've initialized like 1000, but we do a pop instead of a store?
Well, and then you get pop, you first, I don't know, about you try to pop, you go first.
Well, that goes back into it's a last in, first out memory construct. Like if you try to do something else, then it's not this.
Oh, okay.
That's what. Yeah, and again, see, the reason for that is because it keeps things simple, right? Because if I know it's this construct, then I know that, the last thing I put in, that's the first thing coming out. Right, so yeah. Yeah, again, this is sort of like the basics and how you do it. When we get to subroutines, you're gonna see a reason why it's this way. Okay, so I guess we're just about ready for subroutines. Are there any questions before we go to subroutines?
Is this applicable to software board? Then I know that's the last software.
Yeah, the question is this relevant to software 4? I made it relevant. Because software 4, the reason we skipped software 4 is because software 4 doesn't really go over anything new at the point that software 4 comes up. It's kind of a outlier, if you will. It's kind of extra. But what I did is I made it part of the final project software where I combined it with subroutines. Yeah. And I'm going to talk about that once we're done with it. Okay, but everybody okay up to this point? So I think I'll go another like 15 or 20 minutes and then we'll take a break, about a 5-minute break. And we'll continue after that. But again, just some basics on subroutines and then we're going to do some examples. Okay, first of all, subroutines are useful when you have repetition. Repetition. Who's a good speller? Repetition, is it R-E-P-E-T-I-T-I? Is it like this?
Yes.
For some reason, that didn't seem like that was an benefit. Okay, so it's for things that you often do in software. So, right now, not using subroutines, right? Because you don't know about subroutines in assembly yet. If you wanted to do something over and over again, right, you'd have to do like a copy and paste in your program. You guys have a question? That's all right. So yeah, things that you do over and over again. So, some examples are like multiply, divide, sorting maybe. This one will probably come up in your final project hardware when you go to program your order, your working order to do something. And that's like having a subroutine for a delay, right? Because you might have to delay on the input side to give the user some time to change the switches. And you may need a delay again if you're repeatedly, putting results out to the 7-segment display, let's say. Okay. And I'm sure you can think of other things that, you can make a subroutine for. Now, a question that often comes up is, well, in order to justify having a subroutine, like how many instructions should the subroutine be? Like that's a question that comes up a lot. Like sometimes a person might want to make a subroutine that's only a few instructions, like maybe loading data from a input device or outputting data to an output device, something like that. But the thing you always have to remember is that there is some, like overhead that comes with subroutines, and there's 2 instructions that you always have when you have a subroutine. There's a call instruction and there's a return. Okay. So if you have a subroutine that's only, 1 or 2 instructions, it's really not worth it, right? Because it takes 2 instructions to call the subroutine. If the subroutine itself is only 2 instructions, that's a high overhead, right? Because the number of instructions for the call and return from the subroutine is the same as the number of instructions in the subroutine. But, of course, if you got a subroutine that's got, 10, 20, or more lines, right, then it's very little overhead, right? 2 instructions compared to, multiple instructions like tens and, So anyway, that's what you always have to keep in mind, that, if you just got a few lines, it's probably not worth having the subroutine. But, of course, the more lines, then the less the overhead. Okay, so this is, some of the things you might use subroutines for. Now, like the reasons for subroutines is, one is modularize. You spell it M-O-D. Modularize. Okay. And what I mean by this is, you're taking a big problem and splitting it up into smaller problems. So the big problem split into smaller. Right, and that's a general concept, right? If you've got something, very complicated to do, right? You take that complicated thing and you split it up into smaller things, right? And then by solving the smaller things, it all adds up to solving the bigger things, right? So that's what you're essentially, like the big picture, what you're doing with subroutines, right? You're taking a bigger problem, splitting up the smaller problems, right? Each subroutine is like solving a problem, and then by solving all the little problems, you solve the big problem. Another reason for subroutines is readability. Right, instead of having a huge, program, by splitting it up, it makes it more readable, especially if you use very descriptive subroutine names. And then it also makes it easier to be reusable. And the way it accomplishes this, and we're going to get into it next thing, is by using the alternative register names that we have. And again, that's why I have a hard copy, at least on most tables, of that sheet of paper that has the different alternative names. And this is where, more than using the names, we're using their uses. Okay, because you know, you have these registers that are labeled A that are called augmentative registers, and then you have these registers labeled T for temporary and S for saved. And we've kind of mentioned them, but you know, we haven't really talked a lot about like where you specifically use them. Well, they come up when you use them subroutines. First of all, parameters, the term parameter, those refer to the values given to a subroutine. Okay, to be operated on. So what I mean by this is that, you know, if you've got a subroutine that's going to do multiplication, well, the two numbers that are going to be multiplied, those would be your parameters, right? And those would be the numbers, you know, that the main program gives to that subroutine that's going to do the multiplication. Okay. Return value refers to the results. All right, so again, the multiplication example, you know, the two numbers, the parameters are multiplied, and then the result of that multiplication, that would be your return value from the subroutine. Okay. So now, if you look at that sheet that has the alternative names for the registers, well, A0 through A7, those are, you know, they're called augmentative registers. Those are for the parameters. Right, because when we talk about, you know, values being given to the subroutine, well, the way the main program gives the values to the subroutine is by putting them in registers. Right? I mean, that's one thing at this point in the class that, you know, should be apparent is that for the auditor to operate on anything, it has to be in one of the reg file registers, right? Because that's where, you know, it's the contents of those registers that are going to be operated on in some way by the ALU. Okay. Now, of these 8 registers, okay, A0 through A7, of these 8, A0 and A1, those are set aside for return values. Okay, so any results from the subroutine should be put in either of those two. Now, most subroutines, you know, it's just one value it's going to return, like say the multiplication, right? It's just going to return the result of the multiplication. So if you just have one, you would use A0. But you could have a case like, say with division, like maybe you have a divide by subroutine and, you know, you want the answer of the division along with the remainder. Well, that would be 2 results and you would use A0, A1. Okay. Now, ideally, a subroutine only affects the temporary registers. So ideally, only T0 through T6 are changed by the subroutine. Okay, my triangle with ED, that means changed. Okay, so, you know, that's ideally. We'll get into if it's not ideal. And then also ideally, a subroutine would not change the saved registers. Okay, so saved registers S0 through S11. And did I get that right? Is it S11 or if you look on the sheet there, what's the highest saved register? I did this by memory, so I've taken a chance. Is it? Okay. I lucked out on that one. Usually when I try to remember something, I'm usually off. So yeah, ideally, the subroutine is not going to change any of the saved registers. Okay, and again, ideally, but we'll talk about, you know, if we don't have the ideal case. All right, last thing, then we'll take a 5-minute break, and then we'll look at the code for subroutines. I just want to show you when you have a subroutine, how it would affect a flow chart. Okay, you've been doing flow charts, right? You've done a number of them, so you should be familiar with most of the symbols up here. But we haven't used the subroutine yet. So this is the only symbol you haven't seen before. You can see it's a rectangle with two bars on each end. And you would put the name of the subroutine right in the middle here, like I have. Okay, so that's the only thing that's new that, oh, the other thing that's new is that when you have a subroutine, instead of using starts, you would just put main, and you could put the name of the main program too, if you wanted to. But yeah, this wouldn't be start, it'd either be main or the name of the main program. And then you would have a separate flow chart for the subroutine. And that flow chart would start with the subroutine name. And then instead of ending with an end, it ends with a return. Okay, and we're going to talk about what return means coming up. Okay, so any questions about subroutines up to this point? Because the next thing is to show you some code, but before that, we're going to take a short break. Okay, so you have a question? Yep, I'm going to turn the camera on. That's another reason to take the break. Because I figured if we have a break, I'll probably remember to turn the camera, but I appreciate being reminded, so thank you. So, okay, so let's just take, oh, a question, wait a minute.
Would probably be the sort of like, kind of like functions and like higher level languages. You know, if you ever run into an issue with this, they're like, seems like they're all just like, I get an address, make an address, and then find it. So, already, sort of faster.
Well, you are, I mean, you're right, that in some languages, subroutines are called functions, so yeah, functions, subroutines, same thing. As far as scope issues, I mean, I can tell you in this class, I can't promise that, but I can follow on class. I think that's why they have the, if you look at the special registers in there, they have alternative names, there is like a global pointer. Like there's another one. Yeah, so that probably comes into play there, but I'm not familiar with that, so. Yeah. Any other questions? All right, so let's just take about a 5-minute break, maybe to 10 past, and when you come back, I'll finish with just going over some code for subroutines, and then I'll hand back your midterms. Oh, also I have to talk about the final projects, and then I'll hand back your midterms. Okay?
I don't think that's talking about my. Yeah, I'm always just working that. Oh, this is one button. Yeah, like, you remember that? You hired? Yes, we were. Probably give it back when I drop. Yeah, I was, yeah. Yeah, I know before well. Oh, huge.
It's all,
This, so this part is.
you're gonna have to like. Get rid of handle tag go. It's what it is. Great. You need to hit it with a hammer. You gotta hit it like with a hammer right here. Yeah. That's it. That's yours. Well, you're just. Yeah, I mean, that would be ideal. Big brain, big brain. Hired me. Give me a job. And
I originally thought of doing it that way, but then I thought if I did it that way, I might not show here.
So here, if you want to look. When you're not moving back. So if we wanted to move the stacks, it's complicated.
you want me to put
Please stack more first. Yeah. Yeah. Because you can always do it. One is doing stack for. This is. Here, or either one. Then you're not moving back.
They had a.
So here's. Then you're pointing at the same address. Okay, I see. And then you don't get anything. Yeah, I think it's second. Yeah, or you could eliminate all that.
Oh, so
Keep track of it.
Well, that, I think, that goes again, you know, again, like. Public they feel something like the. Yeah, you're right. Like, back on the offset, because yeah, that's originally what I had, right? It wasn't. Yeah. But that's why I was put in fact what we went. Yeah, again, it's just really no concept. Right. Yeah, it's always done. You know, but I don't know, like, we could do it. But you can get better. Yeah, because this, I think it is. Here by. Yeah. You need circuits. Yeah. We have, we're behind. Yeah, we haven't gone to vote any thoughts about we was supposed to do. You've been in the week afterwards.
I did. But like, it was scary. That's and then like all of a sudden it's like. That I skipped. Oh, that's what you want.
Okay, so why don't we start up again? I think it's been about 5 minutes. Okay, so you ready to start? So let me give you a few examples. Now, these are generic type of examples, but I'll give you a couple of examples of a subroutine, and kind of like some of the issues that come up. And then also to show you where the stack can fit in, along with these different registers we use for particular uses. So I have one example that's just sort of a straightforward, a main program's calling one subroutine. And then I have another example where a main calls a subroutine and that subroutine calls a subroutine. Okay. So let's look at this one first. So I put this assembler directive just to remind you, we talked about these directives. Now, this .text wouldn't be necessary if all you had was code, right, in your RARs. If you had some data, like say a data array or something, then you need this. I just put that as a reminder. You don't necessarily need it, right? Because if all you have is code, then it defaults to that. Okay, so you can see here I got a label main, and so you got some code in your main program, and then somewhere in that main code you're going to call, or you're going to go to the subroutine. And in assembly, the way that you go to the subroutine is you use a call instruction. Okay, and this call instruction, it's a pseudo instruction for a type of JAL. And remember when we did the data path, and this is the reason why I have the otter diagram on your table. Remember when we did the data path for the JAL, a real key thing in this instruction is the L. Like, what does the L mean in JAL? It means link. And remember, in the hardware, what that meant, right, if you look at your otter diagram, see how there's a connection from after where the program counter has been incremented by 4, right? It goes up to the mux that's right above the right data input of the reg file. So remember, what that instruction does is that it will take the address of the next instruction after where the JAL is, which in this case is the call, right? So it's going to take this address, right? PC plus 4. Oops, let me get my blue marker. I want to put new stuff in blue here, so PC plus 4, right? It's going to take PC plus 4 and put it into the RA register. What does RA stand for? Return address, right? Because after the subroutine is finished, it wants to come back to here, right? So it's got to save the address of that instruction, and it does that by putting it into the return address register. What number register is that? It's 1, yeah. It's register 1. Okay, so again, the whole reason it does this is because that's where it's going to come back to after it's done with the subroutine, right? So see, once it hits this instruction where it calls the subroutine, it's going to go down to where this label is. Okay, so you're going to run your subroutine, and then when your subroutine is done, it hits this return. The return is another pseudo instruction, which is a JALR instruction. And that's going to take it back to the instruction right after the call. Now, the other part of the JALR is that it's also taking the next address after the return and saving it, right? Because it's got an L. And anytime there's an L, right, whether it's JAL or JALR, it means link. And link means it's saving the PC plus 4 address. But notice that in this pseudo instruction for return, it takes that address, that PC+4 address, and it just sends it to register 0, right? X0, register 0. And what do we know about register 0?
It's always.
It's always 0. So see, it's just taking this address after the return and sending it to 0. And why do you suppose it's doing that? Because what's going to happen when it sends it to register 0? It just becomes 0, right? So we're not going to use it for anything. And the reason we're not going to use it for anything is because there's nothing after the return. And we send it to register 0 so we don't possibly overwrite data we care about, right? Because we got to send it someplace. We got to send it to some register. And if we were to send it to some other register other than register 0, we could possibly overwrite data that, you know, we're concerned about. All right. So we send it to register 0 just so we don't overwrite some data someplace else. And we don't need it anyway, because we're not going to return to after this anyway. Yeah, does that make sense? Okay, now I've left out something intentionally. The add eyes over there, I did leave out intentionally. That was a correction by Diego that I appreciate. But here I intentionally left something out. What do we need to put here? This is between the main program and where our subroutine is. Because if I don't have anything here, what's going to happen once I'm done with my main program?
It's gonna go down to the summer.
It's going to run the subroutine even though I didn't call it, right? So how do I prevent that from happening? Actually, you had to do this in an earlier class. It was a different situation. Well, it wasn't subroutines, but it was the same sort of thing that you didn't want, you know, after one part of your program was run, you didn't want it to go into another part of the program. So what did you put there to prevent that? Jump back. Yeah, just jump back. It's called a trap, right? Remember we called that, right? You could just do something like, black mark is really on there. You know, you could just put like something like a label done, and then just jump to done. And remember, we called this a trap. Because it's just going to stay on that line. Okay. All right. So, any questions here? I mean, the key thing, I guess, is just understanding what this JAL instruction does. Again, the key thing is understanding what the L means, right? And I think if you look at the data path diagram that we did earlier, where we're saving that PC+4, and again, we're saving it because that's where we want to return to. And then this return instruction is just a pseudo instruction that will return us to that address that was saved in the return address register. Okay, so everybody okay? All right, so let's go to this example. Okay, and here in this example, you'll see something arises that's a little bit of a problem, but we'll show how to solve it. Okay, so in this example, we have a main program calling a subroutine, but then that subroutine calling another subroutine. Okay, so we're in the main program. It's going to call subroutine 1. So again, this call is a pseudo instruction for JAL. So the PC+4. So you know this address right here, right? The address of the instruction right after the call, that's going to be saved in the return address register. Right? Our okay. So now, what am I going to have to put here again? In between the main and where this, yeah, I'm going to have to do another trap. So, you know, another trap here. You know, for the same reason as we talked about here. Okay, but now subroutine 1 gets called. So, you know, it's got some instructions here, and then it's got a call to subroutine 2. So at this point, again, a call is a pseudo of a JAL. So it's going to say PC+4 of this instruction. And again, it's gonna put in RA, which is register 1. Okay, so subroutine 2 gets called. It's gonna do subroutine 2. It hits this return. So where's it gonna go once it hits this return? Because what's in the return address register at this point? Well, that was the last thing that was saved, right? This address of this instruction was the last thing that was saved in RA. So this return will take us back to here. Everybody agree? Okay, now it executes these instructions. It hits this return of subroutine 1. Well, what's in the return address register? See, when it hits this return, we have the same return address, right? Because this hasn't changed. So it would just go here. It wouldn't go back to the main program, right? Because the main program PC+4 was overwritten, right? Because your PC+4 return address, it put in that same register, right? So if I have this return address in the return register at this time, when I get down here and it puts this address into the return address register, well, this gets overwritten. So you see, that's the problem here, is I would never get back to the main program. All right, so does everybody see the problem before I show you the solution? Because the solution is using the stack. Does everybody see the problem? Well, you can solve this by using the stack, because what you would do, I need a different color here. We'll use green for solution. See, what we could do to solve this is right before, or the first instruction here, once we go into subroutine 1, is I would push the contents of the return address register, right? I put that on the stack. And then before I return, I would pop it. Right? So that would put this PC+4 of the main into RA when I hit this line, once I come back from subroutine 2. Okay, so that's an example of the use of the stack, is that when you run into a situation like this where your RA register is going to be overwritten, you can save that return address. Okay, and then after it's been used, take it back off the stack. Did you have a question? Okay, that's great. Now, another use of the stack is, we said down here that ideally you only want the subroutine to change temporary registers, right? You don't want to change any saved registers. Well, it's possible that, it's possible that if you got a number of subroutines that you're going to run out of temporary registers, right? I mean, that could arise. So if that happens, one solution is you can use the stack, that you can put temporary registers onto the stack, temporarily, if you will, and then, pop them back off after that subroutine is finished. Okay, so that's really like the main uses of the stack is, when you have subroutines, it's useful for saving a return address so it doesn't get overwritten. And then it's also useful for, if you run out of temporary registers, that you can just use the stack for, temporary storage, if you will, of those contents of those temporary registers so you don't run out. Okay? So any questions about anything? Because the next thing I want to do is I do want to go over the grading criteria for the final project, because Like we talked about last week, Thursday is an open lab. So what I mean by open lab is that, the lab is open, but you're not required to be here. I'll be available on Zoom. I'm not going to be here on person on Thursday. And then, the next 2 weeks are devoted for you to work on your final project software and your final project hardware. So I want to go over the grading criteria for the final projects. You have a question? A way to get into the. Well, there's a code. Yeah, it is. So, the door lock here, it's like a code, and I hated it. You had it right on the board. Man, it's 16 something, isn't it? Does anyone have it? Did I not write it down? I thought I wrote it down again. I think it's 689. Okay, 6, 8, 9, 6, 8, 3. Okay, yeah, so that's the code. You gotta get in here now. Of course, the building has to be open. I'm pretty sure the building is open like during the week from like 6 in the morning till probably like 9 at night or something like that. Weekends, I think it's only open on Saturdays, but a lot of times, like on a Sunday, you can get somebody coming in and know what channel. Okay, but let me go over the grading criteria. And this is on Canvas. But I guess it's supposed to rain later today. Okay, it's coming on. Okay, so first, the software final project. And I kind of talked a little bit about this, that I took software 4, which was something we skipped over, and I modified it where you have to use subroutines. So first of all, down at the bottom, I'm assuming because for the software part of the first, for the final project software, it's still 2 people. Okay, and I'm assuming it's going to be the same 2 people, in the software groups that it has been throughout the quarter, unless you tell me it's going to be different. So if you don't tell me anything, and if it's going to be different, let me know by the end of this week. But if you don't tell me anything, I'm just assuming it's the same 2 people that have been doing the software together during the quarter. But as you can read here, you're to write an assembly language program that chooses between 2 subroutines based on a value at this address of real memory. If the value is 1 at that address, then subroutine for part 1 of software number 4 is run, and if it's some other value other than 1, then it's part 2 of software number 4. And each person in the group is responsible for one of the subroutines. Okay, so, and you got to tell me which person is responsible, like in the comments. So there's 2 people. This person's responsible for subroutine 1. This person's responsible for subroutine 2. And then as far as what you submit, it's the same as what the software assignments have been as far as the criteria, but there's one addition, and that's because you're using subroutines, you need more flowcharts. So there should be a flowchart for the main program, a flowchart for subroutine 1, a flowchart for subroutine 2. Let's see, is there anything else here? Oh, and then also add to what's in software number 4, add to that 0 should be displayed if the result is 0. And also some error message should be displayed if you're dividing by 0. Okay, so these 2 things here were not in the, it's not in the original software number 4. So, basically the final project software is software assignment number 5 or number 4 that's been modified. It's been modified in a couple of ways, right? Because you got to use subroutines and also what I have listed here. And again, the grading criteria is the same as what the software assignments have been, but you have 3 flow charts instead of just, single. Flow chart. Okay, so is it clear what's being asked here? Yeah. Everybody's good? Okay, good. All right, so let's look at the hardware. And this is due March 10th. So this is due a week from Friday. Remember, hardware 6 is due this Friday. And due last Friday, which is March 17th, that's the last class day before finals week, is the hardware final project. So this is where you can have up to 4 people. But you have to tell me, okay? If I don't hear anything, I'm gonna assume it's the same 2 people that have been doing the hardware assignments together throughout the quarter. So if you're gonna have, 2 different people or 3 people, 4 people, or if it's gonna be 1 person, I have to know. There are no groups greater than 4. If I get a group of 5 or more people, that's gonna be an automatic failure. So don't do any funny business, okay? 4 is the maximum. So far I've only had 1 group in my 3 to 6 section that has notified me and said, hey, it's gonna be these 4 people. So, tell me as soon as possible. I mean, at the very latest, the end of this week. Okay, so for the final project hardware, you're to make a video. And in the video, you need to show that your Otter passes that all test mem file on the sim in Vivado. And if you watch my video that I have up on Canvas under meeting 12, I show you exactly how to do it. So you just basically have to do the same thing that I do in my video to show that your Otter, is passing the all test mem test in the simulator in Vivado. And then also, same video, okay, it's only 1 video, it's just 3 different things you have to show me in the video. Okay, you also have to show me in the video that on your basis board, it's running that all test mem correctly. And again, I show it in my video. Okay, because what this tells me when I see that it's doing what it's supposed to on the basis board, that tells me your Otter wrapper is connected correctly to your Otter CPU, right? The sim of your Otter CPU in Vivado, that shows me your Otter CPU is all working. Okay, so that's 2 of the 3 things you got to show me in the video. Then the other thing, the third thing, is now you program the Otter to do something. Okay, and it can be any of the assignments you did during the quarter, or it can be an example I did in class, but it's got to be something, we did in class. So it's, really the only modification you're really going to have to do, provided you have something that already works, which I know everyone does because everyone has completed at least 1 software assignment, and most people have done all of them. The only thing you would have to add is like a delay, right? A delay on the user side, if give the time for the user to change switches, and or a delay on the output side if you're outputting to the same output device, right? You need a delay between your outputs. Okay. All right, so those are the things you need to show. And, like I said, 1 video, try to keep it between 3 and 5 minutes. I mean, if you go a little over 5 minutes, I don't mind, but if it ends up being like, 8, 10, 20 minutes, something like that, it shouldn't be that long. Okay. And all group members have to be seen in the video at least for a split second. Okay? It doesn't have to be like anything long. You just show someone's face, I got to see who the group members are, okay? And then as far as what you submit, besides the video, submit a hard copy of the assembly language program fully commented. Now, this is where most people lose points, okay, with what they turn in, is they don't comment their code or they don't fully comment. It should be commented so that when I look at it, I can easily tell what's going on. Also it should be commented so that if you come back and look at it, a year from now, you'll know what you did a year earlier. Okay, and remember to include the team members' names at the top of the program, as part of the comments. And then I do want a zip file of all your Verilog files and or system Verilog files, depending whether you use system Verilog or Verilog. Let's see. And those files at the top, there's like a title, right, at the top of those files, and it's gotta show a name, right, a group member name, and it's gotta show the date and the time that it was created. Okay, if that's missing, like, whether it's, a mistake or not, it doesn't matter. If that's missing, you're not gonna get credit. I have to see the person responsible. I gotta see the day and time that it was created. So don't, or make sure that's there. Okay, that's not a small thing if it's not there. Okay, and then, let's see, what else do I have here? Oh, and then also your Verilog, file should be fully commented again. Okay, and then there's a peer evaluation. I'll show you the form coming up. You have a question?
I have like two quick ones. So
Okay.
if it's a group of four and you wanted like the names to be on top of the files, like,
It doesn't have to be everybody's name, just a name.
okay,
Like, I'm expecting that I'm gonna see like different names, right? Because I would imagine that as you troubleshoot, you might find that this person's reg file is working and this other person's isn't, so you can use that person's.
Okay.
But yeah, it's gotta be a group member, of course. Okay, it can't be someone outside the group, obviously. I hope that's obvious. Okay, and then day and time.
Yeah, and also, last question is, I don't see like there's like a formal report for the content itself, instead of just the peer evaluation.
Say that again?
Like there's no like specific format report for like the code for like the whole hardware setting, like there's no like,
Well, it's just that you're turning in, the actual files that you ran. That's why I said put it in the zip.
so yeah, so the only like written thing would be the peer evaluation form.
See, the only written thing, let me think about that. Is there anything,
But there's the video, there's
yeah, there's the video,
the zip file and then.
the zip file, there's also, well, this is your assembly language program. I mean, you could take this right out of RARS, right? Let's see, I didn't specify here whether it should be out of RARS or it should just be the MEM file. Let me think about this. A hard copy of assembly language program fully commented. Yeah, this can be, because this is the program that you're running on the Otter once it's working.
Okay.
So this can just be, let's see. Let's see. You've had to do this for the software
Yeah,
assignment.
it could be like any software.
Yeah, so it can be like any of your software assignments, right? You just took like a screenshot, I would imagine, or is that how, or you snipped it, I would imagine. Is that how most people did it? I don't know. I haven't been grading the software assignment. So how have most people been submitting the code part of the software assignments? Do they take like a screenshot or? Oh, okay. So they go like in a text file and then.
Copy paste text in your report.
Okay. However you've done it in the software assignments is fine for this. That everybody, does that make sense to everybody? I mean, the most, like I said, the most common reason people lose points on the material they submit is they don't comment things, or either they don't comment at all, or they just do it very sparsely. Okay, so like I said, you want to make sure that you comment in such a way that I can look at it and I can go, oh, that's what the person's doing, right? Because you gotta think like, like when you're working in industry, you gotta think like a boss, right? When you're in school, you gotta think like an instructor, right? I mean, there's an infinite number of ways that you can do these different examples. I mean, I suppose I'm gonna see a number of different examples, and even if it's the same example, it's gonna be different, right? So, I can't just look and say, oh, it's doing that, right? I mean, I gotta have some comments. Otherwise, it would take me forever to see if it's doing what it's supposed to do. All right, like I said, there's a peer evaluation. I'll show you that form coming up. Now, the grade criteria. All right, so this is how the grading criteria goes. If there's a working otter, so that means when I say working otter, it passes the all test mem in the simulation of Avado. It passes the all test mem on the basis board, and you programmed it to do something and it does what you intended to do, program. See, that's what I mean by successful audit, and that can earn up to an A. Now, the reason why I say up to an A is because what could subtract from that is if the material you submit is not fully commented, or there's some other problems with it, or you get a poor evaluation from your peers, you know, those types of things can subtract from the A. So, you know, that's why I have up to an A. Okay? Now, if you have, let's see, if you have an auditor that passes the all test mem on Vivado, it passes the all test mem on your board, but for whatever reason, you can't program it to do something. Or, you know, you go to program it to do something and it doesn't work the way it should. Maybe it partially works, okay? That can earn up to a B, okay? But again, the reason I put up to a B is because there could be something submitted that's not, you know, something missing or not commented, whatever it may be, or evaluation. Also, you need to include a chronological list of the troubleshooting you did to try to find what the problem is. Okay. Okay, the next thing is, if you have an auditor that passes the sim on Vivado, but it doesn't pass the all test on the board, well, that can earn up to a C. And again, you would have to chronologically list the troubleshooting. Okay, if you have, let's see, what's this last one? Okay, the last one is, you know, basically the auditor's not working in the sim, well, if it doesn't work on the sim, it's not going to work on the board. That can still earn up to a D if you chronologically list the troubleshooting that you did. Okay, and then the last one is, again, same as up to a D, that, you know, it's not working in Vivado, it's not working on the board. So therefore, again, you couldn't program it. And you don't give me a chronological list of the troubleshooting you did. Well, that would be a failing grade. Okay, so are there any questions on the grading criteria? Does everyone understand what I mean by up to? Does that make sense? Okay, I mean, hopefully everybody gets theirs working. That's what I'm hoping for. And hopefully they can program it to do something, because that's really what the crux of this course is all about. And like I said earlier, or last week, you are evaluated on being able to find the problem with the auditor, because you will have problems. There's just no way around it. But again, I provided the resources to help you. Dr. Hummel has that video that shows you the process of troubleshooting. I made a video that shows you, you know, what to look for. So what I'm here for, and also, you know, Derek, I haven't talked to Derek yet about it, but Derek may be available during the last 2 weeks to guide you in troubleshooting, but we're not going to find the problem for you, okay? Because you're being evaluated on that. So, you know, what I mean by guide is if you're having some sort of difficulty, you know, I'll ask you what you did. Well, what did you try? You know, what have you been looking at? And then I'll say, oh, well, maybe you should try this. Okay, or look at this. You know, that's what I mean by guide. I'm not going to sit at your, you know, I'm not going to sit and look at your code and say, oh, there's your mistake. You got a 3 instead of a 2, or whatever it may be. Okay, does that make sense? And again, that's the reason why I'm allowing up to 4 people, because I realize this is not easy. Like I said, when I troubleshoot my auditor, and I have experience troubleshooting, now I'm much better at troubleshooting hardware than software, I'll admit that. But still, I have a lot of experience troubleshooting, and it took me a whole afternoon. Like I started around lunch one day, and I thought I'd be done in an hour, and it wasn't until like after dinner time that I finally had it all working. I mean, it took a while. I had like, you know, almost probably a dozen errors. Most were silly, okay, but there was one, like I talked about, the reg file, that, you know, was driving me crazy. And I'm sure you'll have something that drives you crazy, you know. But that's why engineers get paid a lot of money, right? Because we're problem solvers, and a lot of times problems are not easy to solve. Right? But the only way you learn troubleshooting is by doing it. You know, there's no other way around it. So, okay. Oh, let me show you the evaluation form, and I will hand back to you. Okay, but this is the evaluation form. Okay, so every person has to pass one of these in. If someone doesn't pass one of these in, they're going to get deducted points for not passing it in. So, you put your name and then, the maximum team members you could have is 3, the maximum group is 4. So you just rate the person on a scale of 5 here, exceptional, above average, average, below average, poor. And like I put here, please provide an honest, objective evaluation. So what I mean by that is whether you like the person or not should not come into play, right? It's just, how is that person as a team member? Did they do their share? Were they easy to work with? Stuff like that. And you have room here to make comments. Okay, you're gonna have to do this in industry. I mean, it's done here at Cal Poly. I mean, every 3 years I have a colleague come in and they watch me teach and they make suggestions and, constructive criticism. So, it's something you gotta get used to. So you might as well have some practice now. All right, so any questions about anything today? Oh, question. Yes, yeah, one submission per group. Okay. No, I just want to see one person's name. I mean, if you put more than one person, I guess that's fine. But as long as there's at least one person from the group, along with the date and the creation time, it should be fine. Yeah, that would be the ultimate. Is everybody in the group gets their own auto working. That would be great. But yeah, even if that's the case, you just got to pass in one. Because it's a group thing. Also, we have to go on that. Get it worked out. That's a good question. Let me think about that one. So you're saying like if you took the divide by wrapper and changed it so it's a lower frequency, and that lower frequency okay, but not at the 50 megahertz. You're talking like make it run faster. Oh, run faster. Why would you want to? I would. I mean, you can, I suppose, but you're making it harder on yourself because if it works at 100 megahertz, it should work at 50 megahertz. But if it, I want to know faster. Okay, well, yeah, I mean, that's okay. If you want to, what I would suggest is get it working at 50 megahertz, turn that in, and do whatever you want because you never know. You might try to run it faster. I don't know, something happens to your board or something. You get it to work at the low. Who knows, right? So I would play it safe. Once you have it working, submit it. You know how things go, right? Well, a quick story. Did I ever tell you the story about the school I went to? I went to University of Massachusetts for my engineering degree. But anyway, at that school, that a long time ago, they didn't have like a senior project like Cal Poly does, but you were expected to do like some major project in one of your classes, sort of as a finale kind of thing. So anyway, back then the state-of-the-art microprocessor was an Intel 8085. It's an 8-bit processor. I'll show you how long ago it was. It was right on the cusp of them going from 8-bit to 16-bit. In fact, after I graduated, a year after I graduated, 16 bits for the norm. But anyway, I wrote a basic interpreter. It was written as assembly for an Intel 8085 that would take any basic program. I don't know if you've ever heard of BASIC. That was a program back in like the late 70s, early 80s. It would take any instruction from a basic program and run an assembly. Right? So I got the thing working right. And it's the day before it's due. It's like due 10 o'clock the next day. And my friend Brian, we did all our work together. I'm like, hey, Brian, can you just look at it and see if you see anything, that I could, fix up like comments and stuff like that. So anyway, he looks at it and, this is before cell phones and stuff, right? So later that night, we're talking on the phone. He goes, oh yeah, I looked at it. Looked good. He said, I made a couple of like, just minor like corrections, like I had grammar errors or something in the comments. He did nothing to the go in the next morning, 7 o'clock, right? It's due in 3 hours. Crashes. Like it won't even like come up. It won't run at all. It just crashed right away. And I'm like, what? I don't know. So I'm panicking, right? Because it's like due in less than 3 hours. Well, make a long story short, I found it like an hour, an hour before I had to turn it in. When he was changing some of my comments, he accidentally changed like an immediate value in one of my instructions from a 0 to an O. And you know how hard that is? Like back then, the only difference between a 0 and O was one was narrow, like the 0 was narrow and the O was a little wider, but it was like really close. Okay, so anyway, that's why I say once it works, submit, submit, because you never know what might happen. So. All right, so any other questions before I turn back to midterms or hand back to midterms? Okay. So